Hey everybody, let's do a little bit of review. So for rotational dynamics, let me just make up an example. Let's say you have a pendulum. So like this is a test prototype for a wind turbine blade or something. Okay, so it's basically a bar. Let's see, there's length, this bar is length L, and then, so it's a bar like this, and then the mass, I'll just call it M1. Okay, and then a slab like this, and then I'll label it like here to here is whatever distance B, here to here is A, and this is mass M2. Okay, and then let's say it swings like this. What's the angular acceleration? And I'll just label this as some angle. Okay, so how do you get the angular acceleration? You draw the free body diagram, right? So there's the free body diagram. All the forces acting on it. So there's the bar has mass, so then it has a weight. The slab has a mass, so it has a weight at the center of mass. So this is at the center of mass of the bar. This is at the center of mass of the slab. And then there's a hinge up here, right? So there's some normal force at the hinge. I have no idea which direction. Some normal force. Some direction, we don't know. Okay, so that's it. This is the free body diagram. Let's pick coordinates however we want. Let's see. I am contemplating, this thing is going to rotate that way. So I kind of want to make, I mean, you don't have to, but I'd like to make clockwise positive. So if I make this way Z, if I make this X and that way Y, X cross Y would be into the page, which would be clockwise. So then Z would be into the page. So it's basically, it's rotating in the positive Z direction. Okay, so some force is X, some force is Y, you know how to do that. Some torque about, I picked the origin here. That wasn't the only possible choice. You can choose your origin wherever you want, and you can sum torque about any point you want. You can sum torque about over here or over here, here, anywhere you want. There's no wrong choice. So I'm going to sum torque about the hinge over here, which is where I put my origin. Okay, so the torque about here due to the normal force is 0 because it's acting right there. Okay, the torque due to M1G would be, here's the angle, so the lever arm is over here. So it's, and then it would cause a torque going this way, right? Positive. So it's positive M1G times the lever arm, which is here to here, which is opposite the angle. So that's L over 2 sine theta. Okay. And then there's torque from this force, which would go this way, also positive, so positive M2G times this lever arm right here, which is L plus B over 2, right, again, right here. This is L here to here. Then the center of mass is in the middle, so here to here is B over 2. So L plus B over 2, but then see how it's opposite the angle? So sine equals I alpha. Which moment of inertia is this, though? Because I sum torque about the hinge, this moment of inertia also needs to be about the hinge. Okay, so then to solve for the angular acceleration, just move this in the denominator, and then we're done. But what is the moment of inertia about the hinge? So how do we do that? So it was a bar. I'll just draw it kind of vertically like this. And then that slab. And then if the coordinates were which way? Like this. Okay, so okay, there. All right, so the moment of inertia about the hinge, which is right here. Okay, so what's the moment of inertia about the center of the bar? Right here, 1/12 ml squared. So about over here, it's 1/12 ml squared. But we want to rotate about the hinge. So we have to do parallel axis theorem. So plus extra. How much extra? The mass of the bar times the distance between these two parallel axes squared. So that would be L/2 squared. Okay, now the slab, the center of mass is here, and the moment of inertia about the center of mass of the slab is right here. 1/12 mass of the slab, and then a squared plus b squared. Okay, but that's here. We need it to be here. So plus extra. How much extra? The mass of the slab times the distance between these two parallel axes squared. Okay, so how far is this? L plus b/2, right? Because here to here is L, here to here is b, here to here is b/2. So L plus b/2 squared. So that's the moment of inertia about the hinge. Okay. How about some more practice? Let's say we take that same problem. There's the wind turbine blade, and then we release it from rest. So it's at rest, and then it swings down over here. How fast is it going? The angular velocity. Now, could you just take the answer here, like if we solve for alpha equals something, and then use kinematics for constant acceleration? Is this acceleration constant? It is not, because the entire time the angle is changing. So the angular acceleration is not constant. It's a function of the angle. So we wouldn't be able to use kinematics for constant acceleration. You could integrate over the angle. That would be fine. Not over time, because it's a function of angle, right? So you have angular acceleration as a function of the angle, but then angular velocity is like this. So then if you integrate, how do you integrate? Right? So again, this is not a function of time, it's a function of angle. But you have to integrate over time. So how do you do that? You could use the product rule and the chain rule. So then this is d omega dt, but then you can do the chain rule like this. Right? See how that's the same? And then what is that? That's omega. So then alpha is omega times d omega d theta. That goes here. So, and then you can integrate over theta instead. So that's a long-winded explanation for something we can avoid by doing energy way. Right, so let's try the energy way here to solve for the angular velocity. How do you do it? So let's say there's no friction in the hinge, so energy is conserved. Okay, so how much energy initially at rest over here? So it's at rest, no kinetic energy, only potential energy. But how much gravitational potential energy depends on where we pick the datum. So totally up to you. How about I just pick one datum over here, just to make it simpler to explain. So for the bar, the center of mass is here. For the slab, the center of mass is here. So how much gravitational potential energy? They're both below the datum. So negative m1 g, and then how far is this? L over 2 cosine theta. Okay, now for the slab, below the datum, m2g, how far is this? L plus b over 2, quantity, cosine theta. Okay, so that's the gravitational potential energy before we let it go. And then afterwards, it swings over here. So afterwards, it has kinetic energy, 1/2 I omega squared. But which I is this? So now it depends. If we say the moment of inertia about the hinge over here, and then plus 1/2 mv squared for the velocity of the hinge. So that would be the kinetic energy of the hinge translating plus rotating about the hinge. What is the velocity of the hinge? 0. So then it's only this. And we just solved this earlier right here. Okay, so that's kinetic energy, and then potential energy for the bar right here. How far is this? Below the datum, minus m1g, then how far? L over 2. And then for the slab right here, how far is that? L plus b over 2. So minus m2g, L plus b over 2. Okay, right there. Solve for omega. That's one way, or let me recycle this, except I'm going to change the kinetic energy part. Okay, so see how I had moment of inertia about the hinge, velocity of the hinge. What if I did moment of inertia about the center of mass of the pendulum, and then the velocity of the center of mass of the pendulum? This is also correct. You'll get the exact same answer. What is the relationship between omega and the velocity of the center of mass? The velocity of the center of mass is r omega. R meaning the radius. So if the center of mass is, let's say, over here, right? So then right here, this radius, r, that. But how far is that? Where is the center of mass? How do we get that? How far is this? Where's the center of mass of the pendulum? Can we get it? Sure, no problem. Let's try it. So one last thing. So where is the center of mass of the pendulum? Okay, so if I call this way the x direction, then what's the x component of the center of mass? It is a mass-weighted mean position. Mass-weighted mean position. Okay, so one more time. Here to here was L over 2. Here to here was L plus B over 2. So say the x component of the center of mass. It's a mass-weighted mean position. So it's the mass of the bar, M1, times the location of the center of mass of the bar, L over 2. Okay, plus the mass of the slab, M2, times the location of the center of mass of the slab, L plus B over 2, divided by the mass of the bar plus the mass of the slab. So if you run this computation, what do you get? Kilogram meters over kilograms. So you get something meters, right? Which is the location of the center of mass, wherever that is. So let's say over here. Right, so this would be the x component of the center of mass, which is exactly this number we're looking for, r. Okay, and then one last thing, what is the moment of inertia about the center of mass? So if we already knew the moment of inertia here at the hinge, let me get rid of all this other stuff. Okay, so we know the moment of inertia about the hinge right here. What is the moment of inertia here about the center of mass? Which one is more? This one is a minimum. The moment of inertia about the center of mass is always a minimum. So this one is less, this one is more. Okay, so this one would be minus something, right? Because this is less. This is actually a minimum. And this one is, this is more. So then we have to subtract how much? The mass of the pendulum, so there's a total mass of the pendulum, times the distance between the two parallel axes squared. So what's the distance between these two? The location of the center mass, which we just found right here. Okay, so that was a lot of review. We covered a bunch of stuff. All right, so keep on practicing. Let me know if you have questions, and I'll see you in the next video.